So, hello everybody, and welcome to this presentation titled Ultra-Low Latency with Java and Terabytes of Data. It's a bit of a strange title because you rarely see the words ultra-low latency, Java, and terabytes without the word not in between. But it's going to be interesting to tell you why this is not there. Okay, I'm Per. I've done a lot of speaks around the world. I think this is maybe my 100th talk. I've been onto Java 1 for like more than 10 times. I'm a writer. I like Java, so I've written a lot about Java. We're a company called Speedment, which is headquartered in Silicon Valley, but most of the development is made in Gothenburg, Sweden, where I'm originally from, as you may hear. So, this is very annoying, isn't it? You've seen it before? Yeah, it's terrible. So I want to talk about the inverse of this. Not slow things, but fast things. How do you make things fast? And I'm talking about ultra-low latency. And what is ultra-low latency? Yeah, because this is my talk, I got to decide. So I said it's about 200 nanoseconds. And what is 200 nanoseconds, really? The time it takes for the light to travel 1 nanosecond is about this, or about the size of a paper. So I guess 200 nanoseconds is pretty much maybe to that and back a few times. That's the time we have to provide a result. And it's apparently a very short time interval. But why do we bother about that? We as a human can't feel the difference between 200 nanoseconds and 400 nanoseconds or 10,000 or 1 million nanoseconds. We don't see that. But of course, just to compute one thing doesn't mean we can provide that result. So maybe we have a series of microservice architectures, or we have an aggregation that's composed by maybe millions of sub-computations. And that's where it becomes very important to keep the latencies down. It's like a domino bricks. So why are applications slow? There are a number of reasons for that. Slow databases, of course, very well known. Data on several nodes and no affinity across data. I'm going to explore that a little bit more. Data is remote in some sense. Or maybe we create unnecessary objects and have problems with garbage collection. How many of you use Java? Oh, almost all of you. Okay, so then you know what garbage collection is. That's good. And maybe lack of parallelism. So I'm going to talk about the easiest thing first, slow databases. We all know that databases can be slow. And of course, if we're talking about ultra-low latency, even though there are in-memory databases, 200 nanoseconds is totally out of reach. Just to look at the SQL query, not to mention parse it, is a much longer time than 200 nanoseconds. So I want to dwell with that. So let's talk about something more that's not so commonly understood. It's when you have data that is low affinity, you can't scale out and have low latency at the same time. If you have low affinity, you can scale out, but then you don't have low latency. Or you can have low affinity and low latency, but then you can't scale out. And I'm going to explain why that is true. So suppose we have two different kinds of objects. We have squares and triangles. And in the real world, we can say that maybe squares are pants and triangles are shirts. And let's keep to the gender stereotype and say that the bluish ones are for men and the red are for women. So then we can kind of divide them and put all the men's wear here and all the women's there, and then we can compute something there and compute something there and combine the result. And everything is good. Our application works. But the next year, disaster strikes. There is a unisex fashion. So now we don't know who's going to wear which shirt. Women might wear the same shirts as men. So what do we do? Everything falls apart like a house of cards. So of course we can have all shirts here and all shirts there. And we can access them very quickly. But then the scale-out disappears because we have to have all shirts on all nodes. So then it's not scale-out anymore. Then it's scale-up. Or we can put some shirts on one node and some shirts on the other node. But then again, we might have to compute something that's on the other side, that's on the other node. And there goes our low latency out of the window. So that's the problem. And so far, I only spoken about 2 different objects and 2 kind of affinity groups. What if we have 8 different objects and kind of 8 affinity groups on 8 nodes? Or what about if we have thousands of different objects and millions of affinity groups and thousands of nodes? Chances are that we end up in this situation. It doesn't work. So they are kind of exclusive. We can't have all of the 3 at the same time. OK, that was that. Now let's talk about remote. Data is remote in some sense. I did this presentation when I was in the US, but you might as well think that the distance might be from London to Frankfurt or something else. The problem is the same. So if I were to send a package from San Francisco to New York, for example, and back again, that's 45 milliseconds. To Frankfurt, from here, it might be 10 milliseconds. It's certainly shorter, but it's the same problem. It's out of reach for ultra-low latency. So let's go to the other extreme. Let's say we have 2 Linux computers, and we connect them directly via a switch. And that's 100 microseconds. That's still orders of magnitude too slow to be ultra-low latency. Maybe if we remove the switch and we just, wire. No, it doesn't work. That's latency. OK, so I had to fall back to this one. We connect to Linux computer directly via a wire, and we do all the tricks and black belt things we can do. We do thread affinity, and we do busy polling and everything. We might come down to 25 microseconds. That's still way too slow. Let's see if I can shake some life in this. Yeah, it worked. Magic. So data can also be remote, even though it's within the same node. So if we have data in another process, it's still remote, at least as I see it. Because just to make a context switch on a Linux computer is maybe 1 to 3 microseconds. And on top of that, you will ruin all your caches and kind of locality that you have in your application. So that's still remote. So that's that. Let's talk about object creation. You create a lot of objects usually when you use Java. And I think this might be the shortest slide you see in this conference, just 2 characters, beside of the headline, of course. And it's just there to illustrate that a garbage collect might take a second, or it might take 10 seconds, or half a second. Doesn't matter. It kind of ruins your ultra-low latency property. So even this guy might be faster than the Java garbage collector, because sometimes a garbage collect can go for a minute or 2. So this is what you can do to kind of provoke this problem. We kind of iterate a billion times, and we create some object, in this case a film. I'm going to show you some examples later on in this presentation, and they are all about films and actors. So that's why I'm choosing film here. We collect them to a map using the IDE, and we just put in the object as it is. So we have a huge map with the film IDE as an index, and we just materialize them on the heap. And that's usually a very bad idea, because we create objects, and each object has an overhead of byte alignments. And when we put things in the map, we have to create a map entry. And also the int is just not an int anymore, but it's the object int. So there are maybe 10 different objects that are kind of added to this problem for each entry. And they each live for a long time, because presumably we don't create a billion items, put them in the map, and then throw them away the next second. We are supposed to have them for a longer time. So the garbage collector needs to look at them several times. And we didn't solve the problem. We just put things there. So we can only retrieve objects using the key. We can't kind of search what we have. So we need to add, for each column that we want to use as a search, we have to add a tree map, tremendously adding to the overhead of the number of objects. So if we want to be able to search on like 10 columns, we have to have 10 tree maps with a billion entries inside each of them. So this is kind of a bad idea. And we're getting from bad to worse because the execution time of the garbage collector is not linear. You know, I'm a coder and I'm kind of introvert. I hate to go to cocktail parties. But when I go there, I see that if you double the amount of person, there's going to be 4 times more handshakes. It's kind of a quadratic problem. And it's the same with objects. Most garbage collector, they have to determine if one object is referenced by another object. And that's also a quadratic problem, similar to the cocktail problem that I have. So what we see is typically this. The more objects you have, the larger heap size and the longer collection time you have. So we'll easily reach into the minutes if you have a lot of data. There are, of course, specialized garbage collectors that are better than this, but this is the usual behavior. Even writing an object to main memory is slow. This is the shortest object I can come up with in Java in byte form. And it's 128 bits. And just writing 64 bits to main memory, that's 100 nanoseconds. So writing an object is 200 nanoseconds, and my entire budget is gone. So creating shared objects, it's not ultra-low latency. So now I think now you are beginning to grasp the gravity of the requirements of being able to produce something within 200 nanoseconds. You have to understand what you're doing. This is another problem, lack of parallelism. You might have 32 CPUs or threads on your CPU, but you're stuck at 100%. This is a very common thing to see. So what is the solution? Well, we think the solution is In-JVM-Memory. And what is In-JVM-Memory? Of course, you know what in-memory is. In-memory is, of course, when the data is in RAM. And the application is kind of remotely connected. Maybe it's a grid, maybe it's an in-memory database, maybe it's an Hcache grid, or maybe it's something else that's distributed. Or maybe in another process. But In-JVM is more than that. It's that your application is actually able to address the data directly. So it's within the addressable space of your Java application. And that's important. This is now a not so modern CPU. Usually you have more CPUs, but this CPU was modern for maybe 3 years ago. And it's an 8-core. And you can see here the logics are here. Here you have the caches, and inside here you have the layer 3 cache, the L3 caches, which are shared between the CPUs. And in here you have some I/O. Maybe it's a memory driver, or maybe it's I/O, pure I/O drivers. And of course, if you access your data somewhere here from the caches within the CPU, you get good latencies. Whereas if you access 64-bit memory, you get 100 nanoseconds. So you can only afford 2 of those to be within 200 nanoseconds. So it's important that your application views, like if you start to think about computer, you might have the computer as such, and you have the hard drive, for example, and you want to keep things in RAM rather than the hard drive. But for me, the hard drive is main memory. This is like accessing something that's on an external storage. I want to live here. You with me? Good. OK, so this is just an exemplary performance comparison between a grid of 4 nodes and our In-JVM solution. So typically, the performance is way higher. That sounds good, but how do you scale this? What if you start off with not so much data and you grow? How are you going to handle it? With a distributed system, you just add more nodes. So there seems to be some problem here. How can we solve that? Well, luckily, memory is cheap. I think it was 3 years ago that humanity passed this kind of threshold, that 1 gigabyte of memory was cheaper than a cup of coffee on Starbucks. So I think that's important to understand. It's getting even cheaper. And actually, you can scale with in-memory. You can go to AWS today and sign up for 12 terabyte RAM. And now you're thinking that this is enormously expensive, but I'm going to talk about that later on. It's actually not. And we have reason to believe that soon we can scale up to 48 terabytes. because that's the way that they increment the memory address space. So you just go there, maybe you notice too small, you pick another one and restart it, and there you go. Now we have more memory. Okay, so let's go and talk about costs. I think the general belief, including my own belief, was that, okay, it's cheap to have memory in your nodes on AWS or any other cloud provider, but the more memory you have, it kind of kicks off exponentially and getting even more expensive the more memory you add. But that's not true. The fact is that it's completely linear. If you use this series, for example, it is completely linear. You pay in proportion of the memory you're using. So what if you have more than 12 terabytes? Do any of you work with data sets that are greater than 12 terabytes today? Some of you do. Good. So then you're interested in what I'm going to say here now, probably. Of course, you can do some kind of high-level sharding. Maybe you have regions, maybe you can divide it in time, or kind of cheat in another way, because then you have really avoided the problem. You can use memory mapping. For example, Intel has something called IMDT, which kind of sits as a layer between your main memory and a very quick SSD device. And of course, that will make your solution a bit slower, but will also provide you with a lot more memory at a lower cost too. So by the solution, you can come up to maybe 30 terabytes or something. And of course, maybe you have a lot of data, but you don't necessarily need all that data to solve the problem that you're trying to solve at that time. You might have data with a lot of sensors, and they measure like 10 different things, but the problem you're trying to solve only involves 3 of them. So then, of course, you don't have to pull in everything and stuff you don't need. Okay, so what if my data grows? Well, chances are that even if your data grows exponentially, the maximum JVM memory size will grow more as time goes by in absolute figures, because the growth historically has also been exponential, historically. So even if you're here 2012 and you doubled here, the max size of RAM also doubled or even tripled. Okay, so this is kind of an illustration. You have very good performance up to this limit, and then you don't have any performance, and this is kind of scale-up solution. It scales forever, but the performance sucks. So that's the kind of trade-off you have. It's okay to have a solution that's slow if you don't need something that's fast. But chances are that you need to access your memory and get data faster than your competitors. That will give you an advantage. Okay, small recap. You can't have these at the same time. But if you scale up, you can have them. Okay, I think this died on me again. Oh, we're back. Okay, so let's look at our solution of this called Speedment. So I'm going to show you a video here. It's just 1 minute long. And so Speedment is something you can have. It solves this problem that I showed you before. Things are too slow. You connect to an existing data source, for example, a database. It will read the metadata. And you can see here to the left, you have the schema of the database. You can do some settings, but then you press generate, and it will generate a domain model for you. And now you can start working with standard Java streams and access these data that you have in RAM. So the streams here are connected directly to RAM inside your application. And it's very easy to use because Java streams are kind of standardized. So instead of using a connection to the database and adding just these 2 lines, we will take a snapshot of the database, pull it into the data in the JVM, and use standard Java streams to access it in ultra-low latency. You can see the speedometer there. Fantastic fast. So it can continuously create snapshots from a data source, and a data source can be pretty much anything. It places a copy within the JVM. Everything is off-heap, so it doesn't create any Java objects. Instead, it lays it out in off-heap memory. And also the indexing of all data is done off-heap. So it doesn't matter how much data you have, your heap will not be affected. All the operations that we have, like finding things or sorting, stuff like that, are order 1 or order log n. I hope you're familiar with the order notion, but it says that it doesn't matter how much data you have, the time it will complete will be largely constant anyway. And it has no impact on garbage collection, so you can fill up terabytes after terabyte. So this is kind of a schematic way of illustrating it. Instead of having a big heap, we put data off heap in a more efficient way. We don't have the usual like overhead in a Java object, like class pointers and monitors and stuff like that. And you end up having a very small heap instead, where you can run your application efficiently. And as I mentioned, the API is not our. We use the standard Java util stream. And since this is an interface, we have made our own implementation of that interface, which connects directly to RAM. So you can use anything in the stream kind of ecosystem. You can use any collector, any filter, predicate, sorting, comparator, whatever that's there. And this is something I wrote on Oracle Java magazine some years ago, maybe 2 years, I think. And an interesting thing is that you can also skip in memory and let it work against a database. That was the main article about here. So you just add the in-memory component, and suddenly everything is 10,000 or 100,000 times quicker. So let's compare Java Stream interface with SQL. Well, you see this select star from film where rating equals PG-13. PG-13 is the American system of categorizing films. It means that you have to be 13 or above to see this. Otherwise, you have to have your parent with you. And the database, and when the database gets this query, it's free to use any resources it has to kind of send back all the film that satisfies this predicate. Of course, it can evaluate all films. And is this PG-13? No. Is this protein? Yes, and so on. But presumably, it will use some kind of index to be able to fulfill this query in a fast way. The same is true with streams. Actually, it looks like we are creating streams with all films, and then for each film, we are kind of evaluating this predicate, but that's not true. This means that we create a film, we create a stream that has all films, and the next sentence here means that we create potentially another stream that only contains those films that satisfies this requirement. And this is kind of a mind-boggling thing you have to think about. It's very easy to fall into the trap and that the stream always has to materialize everything that's there. So this actually does create another stream that uses an in-memory index that can look up this very quickly. Yes?
Is this, so every time, let's say the stream is reading off-heap, and also the filter is also gets put into off-heap again, right?
Yeah.
Whatever the output is. So everything is always off-heap.
No, everything here is off-heap. But once you're, that's the next slide. So that's good thinking. Okay. So what happens after this, of course, is a very important question. So let me take one example. Suppose we are just counting things here. Well, then we don't have to materialize the objects that were off-heap. I think that was attached to your question here. So we don't have to ever produce a film here. We just have to count them. And we can use the index for that. The index knows how many films that satisfies this requirement. So it looks like we are doing a stream, materializing all the films, evaluating the predicate for thousands and thousands of film, and then we're counting them, but we're actually not. We are just saying that we have this stream, and then we can apply some index, and that index actually knows how many films there are that satisfies this particular predicate. So it can return the response immediately here. And this is something I'm going to demo later on. Or we might do something else. Maybe we will collect them to to a collector. If we would have collected them to a standard list, for example, then we have to go off-heap and kind of materialize the object and produce ordinary Java objects from off-heap. But in this case, I have a special JSON aggregator that also can operate off-heap. So actually can decompose this stream and kind of figure out how do I extract the length and title from off-heap without creating films. I'm just reading the length, it's just an int. So I'm just reading an int, putting that off-heap in my JSON representation, and then I read the title, off-heap, and put it in my off-heap aggregation, and so forth. So actually, we don't create a single Java object here. And that's the key to unlocking the speed. Because remember, just to create a shared object is 200 nanoseconds. We don't have that budget. Another cool thing is that you can create kind of semantic joins from RAM. So in this case, we have a film, and we join on language from a language table. And we create a tuple of that. So that creates kind of a RAM representation of a join. You can also have aggregators. You create something on the language IDE, you have a key, and on the film rating, you have a key, and then you compute the average of the length, and you build that kind of aggregator, and now you can use it together with the join stream like this. So they are kind of building components that clicks in to each other, and everything works off-heap. You can, of course, use a regular collector here that you can write in Java, and then it will materialize everything in Java, and it will work. It will only be a bit slower.
How expensive are these? So what if we wanted to have our own collector?
Yeah.
But also use off-heap? Do you provide interfaces?
You can do that, but that's tricky. But you can do it. We provide interfaces for it, but it's not within the usual kind of use case. But it's possible to do it. OK, so what if we want to make things parallel? What if we have like 32 cores, and we want to do this off-heap aggregation? Well, streams can very easily be made parallel. You just add the word parallel, and then it's parallel. So this will create, this aggregator here is parallel aware. So it will create, like if you have 32 cores, we will create 32 sub-aggregators that will compute on each own part, 32 part of the problem, and then all those aggregations will combine to the total aggregation and presented. So we will completely utilize all this parallel computing capability on our server. So now if we have 32, we can utilize this fully here. So let's do a hands-on demo. So what I've done here is that I've downloaded an example database. In this case, it's a MySQL database. It's about films and actors, stuff like that. It's called a Sakila database. You can download it, or you can download it as a Docker instance. It's nothing special. It's just a standard kind of set of data that you can play around with. And what I'm going to do is that I'm going to first run this against a database that I have installed locally on my laptop here. And then I'm going to activate the In-JVM acceleration. I'm going to run the same test. So we're going to see the speed difference between those two solutions. And this is one of the tests I'm going to do. This is exactly the one I showed before. I take all the films, I filter rating equals PD13, and then I count them. Then I also have another one that I'm going to run. And that's the second case when we have everything in the JVM. So go to the initializer, clicking what kind of SQL server you have, what kind of Java version you have, in-memory acceleration, enable, and download. Then you get the POM, and then you can just start off your project. One of the plugins is that you can launch this connection to a database. So that's kind of a graphical tool. You connect to your data source, and you get this kind of application where you can do some tweaking. It's not necessary, but you can do it. Maybe you want to rename a column or rename a table or exclude something that you don't want to use. Or then you just generate, and you have a domain model. And that's where I am right now. So that's what I've been doing before I am at this demo that I'm going to show you right now. So I hope you can see this. It's kind of a small screen. So I'm going to start this before I explain what I'm doing because it takes a while. So here I have, if false, it means that I don't have any acceleration. So I'm going to run this now. Run. Okay, while it's running, I'm going to show you what it actually does. I have two benchmarks here. I really already talked about this first one. The other one is a little bit more complicated stream. I'm going to show. That's where I take all the films, I sort them in length descending order. I skip the first 745. I look at the next 5. I extract an integer, rental duration, and I compute summary statistics. Summary statistics is a standard Java stream function that kind of computes like average, max, and mean on some data set that's in the stream. So actually, map to int creates an int stream, and this computes a summary statistic for the int stream. So this shows also the capability of connecting to the Java stream ecosystem. And now we run it both those streams against a database. Of course, this first one here will be kind of select count star from film where rating equals for PG13, and the second one will be like sort, skip, and limit, you know, how this corresponding sequel will look like. So now we're finished, and the complex stream, we could do about 500 per second, and then kind of more easy one, it's almost 2,000 per second. That's pretty good. This is just a laptop, so I think that's okay. So let's activate in-memory acceleration. And now, that's the only thing I changed. So everything else is unchanged. Still the same streams. So now it's running. This is a framework called JMH. Have you guys run JMH for benchmarking? Okay, some of you has. It's a very good thing that kind of solves the problem with JVM warm-up and everything like that. So what it does is now that instead of running directly, it pulls in everything into the JVM. And I can show you how long time that takes, because that's a question I often get. We're pulling 50,000 entities, and that took 1.5 seconds. And here we can see how much data it took, and on average, 100 bytes per entry. So it's a very dense representation. OK, so now it's running. Now the second is running here, and it's very exciting to see the result. I think I have my, yeah. Let's see, yeah, if I have more time, I can show you even a thousand. So there we are. So instead of 2,000, I'm doing 22 million operations per second. It's another universe. It's incredible. And the more complex one did 500. Now it's almost 3 million. And I'm only using one thread on my somewhat old laptop. So let me do this. This is completely ad hoc here, but let me do this. I tried this before. Threads max. So now I'm using all the 4 CPUs on my computer. And the good thing with this representation of heap is that it's immutable. It wouldn't be possible to have the performance we have unless it was immutable. And the good thing with immutability is that it's inherently thread safe. So you can throw as many threads on this as you want. So now I'm doing exactly the same run, but I'm using all the threads instead of just one thread. Again, it's an old computer, 2015. So let's see where we end up. I kind of scroll down, not to reveal the result here. So now the second run. It runs first a warm-up, because it warms up the JVM, so it can compile everything. And then it runs the actual benchmark. Looks good. So there we are. 8 million for a complex and 50 million operations per second on the simpler one. That's what I call performance. Okay, so this is just one example. Also, with the development of more advanced JVMs, the speed will increase, even for the same set of data and code. Yes, question there? Good question. How will the performance be affected if there is updates going around at the same time? Of course, I talked about immutability, so this is a good solution if you have data that doesn't change so much. If you have 99% writes and 1% reads, you shouldn't use our solution. But if you have a fair amount of updates, you can still use it, because creating a new snapshot is fairly cheap. You can create a delta snapshot from an old snapshot, and if you have 1 terabyte of data, the engine will kind of be able to recycle most of your byte buffers, because this is kind of built around byte buffer, which is a standard Java memory representation. So it will recycle 99.5% of them and create new ones that affect the changes, and then you have a new lightweighted snapshot. So you can do hundreds of updates per second.
Do you apply delta, or do you create the whole snapshot again?
It will be a new snapshot, but it will consist of 99% of the data from the old snapshot. So it's a kind of a delta thing.
Is it like a persistence collection sort of thing?
We don't persist it. You can map it to a file, which then can be persisted, but basically it's a RAM representation. So you should have your source of truth somewhere else.
What I meant was persistent collection in the sense that it will only append the latest changes. It will take the previous snapshot, compare, and append it, or it will rewrite the entire.
No, it will only. Okay. A snapshot, it's kind of a tree of data. So it will only affect the leaves that are affected by the actual update. Okay. So that's why I'm saying that it's kind of a lightweighted thing to do a new snapshot. You don't have to pull in everything from start. You can reuse most of the things. So for example, if you update a film, you add an actor for a film, for example, that's a very lightweighted operation. Even though you create a new snapshot that represents a terabyte of data, 99.999% of that in that example will be reused. So it's just some leaves somewhere in the bottom that will be affected by this update. Everything else stays the same, but still it's a new snapshot. And that snapshot is immutable. But since the immutable snapshot relying on other immutable things, they can be reused because it's immutable. So once you go from immutability, you really see the beauty of it. Okay, so we are expecting that performance is going to be increased even more, even though, of course, we do upgrades that increase the performance of our framework, but we will also benefit from the general performance gain of the JVM. Okay, how do you use this? You can use it with pretty much any database standard out there. You can write a stream that connects to a binary file. A guy even did a Google Sheet connector. So there are basically no limits on what you can do. Anything that can be expressed as a Java stream can be used as an input. You can deploy it anywhere. Of course, you can use Docker. That's actually what we do in our test environment. Or you can deploy on any cloud or on-prem. It doesn't matter because it's Java. You can even deploy on a Raspberry Pi if you want. IDE integration is very simple because a data model doesn't require any magic. Everything is generated, and you can see the code, what's generated. You can see your POJOs, you can see your serialization, you can see everything. And of course, you can deploy it on any web server, like Spring or any of the Java servers out there. Yes, question?
Do I understand correctly, one has to direct all the write traffic to the database and then the read traffic to the memory queue, right?
Well, that depends on what you're doing. But in theory, yes. Usually the database is often the source of truth, and you have kind of a snapshot of the data. So it's usually the case what you described there. So that's correct. Yes?
Do you always have
No, you can use a file or whatever, or a socket or a JSON call or whatever to populate your in-memory store.
Even as a Kafka stream and stuff like
Kafka stream, that's perfectly okay, or your own stream or binary file or CSV file or XML file or whatever. As long as you can convert it to a Java stream, you can input it here. And I haven't seen anything I can't convert to a Java stream yet. So it's pretty much any data.
the initializer you have.
Yeah.
It only seems to have databases as an
That is correct. So you have, in that case, you have to write your own connector. If you have a custom input, like a proprietary binary file, for example, then you write something that converts that to a Java stream with some kind of object. And then you have to, there's a JSON file that you can use to describe the structure of that, and then that JSON file will be used for domain model creation. So it's very easy to do your own kind of adapter. Yes, question? More? Yes?
So is it an implementation of a collection that you build and then?
It's not a regular Java collection, but it's kind of a collection of something. But it's not, it doesn't implement the Java collection framework, but if it would have done that, it would be too slow.
Okay, but you have a collection or something like that.
Yes.
Then you execute the stream function on that. You have your own.
That is correct, yeah. So it's a collection of data, and it's done in a smart way so that you can kind of create streams from that collection in a smart way, using indexes or whatever that's there. Yes? Okay, so the question is, I'm repeating your question because you're sitting far from me, so I don't think they heard it. Do you have to have JDBC connection, or is there some kind of special connection to the database? Is that correct? The question is that, in this case, it's just JDBC. It doesn't rely on any special feature of a database. And that's the reason why you can use it also for any other data source. Of course, when you use JDBC, you also have the metadata there. And that's what's being used to optimize the process of building up the domain model. If you don't have JDBC, you have to do that manually in a JSON file, like if you have a binary file or something. So that gives you kind of two advantages to have JDBC. You get the data, but you also get the metadata. Yes?
Use the off-heap memory, so you don't have to deal with garbage collection. But my understanding was off-heap was slower, but I guess it's not in this case.
Yeah, the question is isn't off-heap slower? Yes and no. If you're using the off-heap as a means to just serialize an object, and then when you need to access that object, you need to materialize it back on heap, then yes, it's slower. But we don't do that. We have a more granular kind of way, so we can actually extract columns directly off heap without having to materialize the entire object. And that's why it's still so fast. So it is true what you say. Previously, in most implementation, you just serialize back everything you have, and then it's slower. But now you can extract things, and we can kind of decompose the stream and see that, oh, I'm only extracting the title and the name, for example. Then I will only read the title and the name from off-heap and not the entire object. The object might consist of hundreds of columns. And as you say, rightfully, that will be very slow if you have to materialize all those 100 columns and maybe only use one. Yes?
And we can read the stream of the data from network and
Yes.
directly off-heap and write it like directly on databases. Or what are the latency or data copy we need?
You can get your data from you can call some socket or HTTP address or whatever. A JSON call, you can call. That's what the guy did with the Google Docs. That's a JSON interface. So you just call the JSON interface, got a long JSON response, query that, and defined also the JSON model at the side, and got everything in and had it off heap and used the querying super fast. So you can do that, yes. Yes?
Do you have sample projects that I can try? Because I can see that you have, there is a free license. You
Yeah.
can try up to 500 MB or whatnot. But if we want to try all the features, do you have like projects that are in GitHub somewhere?
Yes, you can have you can request a trial, which is unlimited.
Okay.
So you can use that and actually try terabytes of data.
But do you actually have like sample
you have when you go to Initialize there, you will have kind of a startup of your project with the main method and everything. So it's very easy to go there. And in the manual, there are a bunch of different examples that you can use.
But you don't have like ready-made examples of like a sample data model in the database in the loading data?
Yeah, we usually use this Sakila database. So all the examples in the manual and all the examples in the wiki kind of draws from this Sakila database that I showed. So if you download that, you can play around with it and use all the examples that we have and learn from there. And more questions? Okay. Thank you so much for your interest.